Today I will not use a lot of time for lecture because I have a meeting at noon time. I may just take maybe 30 minutes and then finish today. I just checked, I noticed I have already covered everything. And you are working on the homework right now, so it covers everything that is needed for the fatigue design. Actually, after tomorrow's exam, we are moving on to applications and also introduction of different kinds of components, such as gear, screw, and different spring. So today, actually last week was the last lecture that you need to know for the fundamentals that are required for mechanical design, component design. You just need to know how to define design equations for failure or fatigue. I will go through, very quickly go through this exercise one more time. And before that, I want to remind you tomorrow we have an exam. And since we only have 1 hour, I won't give you a problem like this, because solving for the shear diagram and moment diagram takes a long time. You need to take integrals and you need to solve for constants. It takes a lot of time, and when you make one mistake, the rest of the exam sheet is not correct. It's very difficult for grading. So for tomorrow, I will give you simpler problems. This is just for you to know. Tomorrow's problem will be simple like this, but probably won't be the same. Just to give you a hint how it looks like. For a simple shaft like this, if you have 2 bearings on the side and some tension from a pulley at this middle point, then when you do the shear diagram, definitely you have a reaction force going down, and then at this middle point, you have a shear force going up, and when you go to the edge, you have reaction force going down again. So that's how the shear diagram would look like. And if you take an integral, because right here you have negative value, so you will have negative slope for the bending moment. And this part you have positive value, so you have a positive slope for the moment. So definitely you will have a moment diagram that looks like this. So right at this point, you have the strongest bending moment. And definitely this is where you need to worry about failure or fatigue. And I will design some shaft so you have different diameter on both sides. So we will have to look at the tables to find out what's the stress concentration factor. Just like what you need to do right here. So I won't just give you one figure. I will give you multiple of them. So you need to be careful to choose the right one. In this case, this is bending, right? So this case, this is pure bending. This is pure twisting. So in that problem, it's pure bending. So from here, this is bending is basically normal stress. So if you are computing for the stress concentration factor, you are trying to figure out how many times greater your normal stress will be if there is a stress concentration effect. So KT is for normal stress, and also for static loading, not yet dynamic, not yet fluctuating. So from here, I will tell you the dimension of the radius, the ratio, the small diameter and the great diameter. You should be able to find the K value. And then, because the problem will tell you this shaft probably is moving in a way such as rotating, or maybe the tension in the belt is changing its amplitude with time, fluctuating. So for tomorrow's problem, there will be dynamic loading for the shaft. So you need to worry about fatigue. Then you need to use a different set of figures like these. And since in this example, it's just normal stress. And in the previous slide, we have K for normal stress and static. Now, if you have notch sensitivity Q, you can use it to compute for the K for normal stress and dynamic loading using the equation right here. Because KT can be found in the previous table. Q can be found in this table. And KF can be determined. KF will be the stress concentration factor for dynamic loading. This value usually is not the same as KT, okay? So here's an example. In the previous slide, KT was 1.76, and because of the condition, we realize the Q is 0.76. By calculation, KF becomes 1.58. So you can see for this low condition, for this geometry, the stress concentration for static is 1.76, for dynamic is 1.58. So once you have those, you will apply specific fatigue model right here, okay? And I like to give problems in cylindrical design because it's very commonly used in machines. So I think that tomorrow I will still use a shaft. So the von Mises stress, the equation for von Mises stress is right here. You need to figure out what's the mean value part, what's the amplitude part. And because we talk about how the shaft could be rotating or how the load is changing with time, you should be able to figure out what would be the average of the stress and also the amplitude of the stress. Okay, so you also need to work on Moore's circle, because for von Mises stress, you need Moore's circle to find out what's the principal stresses. And because the stress changes with time, so the Moore's circle changes with time. Okay, so the first principal stress changes with time. Sometimes it's low, sometimes it's large. So figure out what's the mean value. Figure out what's the amplitude. Use it for von Mises stress. So N right here is the mean value part, or the mean value part. A is the amplitude part. Plug in all the amplitude parts. The rest is just to apply the right fatigue model. So over here, I may give you the equations, but I will not tell you which one is which. So you may see an equation like this, but you don't know this one is for Uihlein or Goodman. So the problem may ask you, hey, use Soderberg. And you see 3 different equations, or even more, just to confuse you. So you need to know, oh, this is Goodman, this is Soderberg. Okay? But at this point, we didn't, in this particular point, it didn't apply stress concentration. Did it? Yes. So the stress concentration is applied when you compute for the principal stress, right here. So in regular cases, you don't see a pre-multiplier in front of the stress. So what are they? They are the K values. The K represent how much higher your stress would be. And each sigma and tau represent different kinds of stress. So I will draw a table to remind you, like what I did here. So you may have normal stress, you may have shearing stress, you may have static loading or dynamic loading, right? So this one you have KT, this one you have KF, oh no, this is KTS. KTS, yes. And this one you have KF, this is KFS. So to determine KF, you need to use Q. To determine KFS, you need QS, right? And if you apply these 4 pre-multipliers to the stress and the shearing stress, what do they apply to? So for static, definitely some values that is the mean value. And because this is normal, right, so this you should apply to the mean of normal stress. And this one you should apply to the mean of the shearing stress. And for the dynamic part, we basically apply these K's in front of the amplitude part, because the amplitude part is the part you have dynamic motions. So basically, sigma amplitude and tau amplitude. So if you, I will not draw this in the exam sheet, but I think this will be a good reminder for you when you do the homework, and if you when you work on your solution process tomorrow, if this helps you, you can try to write it down somewhere. Okay. So once you apply stress concentration, oh, by the way, for the problem I mentioned here, there's no shearing, no twisting, right? So you don't have torque, and your tau will be 0. So for this problem, it's simpler. You don't even need to check the tables on the shearing part, because you don't have tau. Okay. And also, because we solve for chef problems so many times, I still hope you can memorize these 2 equations. But I think I will still provide some equations, and probably including those. Okay? Because from the balance of moment, you get m. But how do you convert m into stress? This is the equation. Okay. So basically, this will be how tomorrow's exam look like, but much simpler. Because I don't want you to I want you to finish complete. Yeah, because if I give you the same problem, some of you may not be able to complete the whole thing. Okay. Any questions? Did you guys do the homework? Is it okay? Yeah. So if you have no problem with the homeworks, then tomorrow should be simpler than the homework. Okay, and let me remind you, I'm sorry, my time is almost gone. So let me remind you what would be the rest of the semester look like. Next week, I will show you autonomous robot, so mobile robot, a huge one. Actually, we have 2 autonomous robots in our lab. Both are huge. And I will show you how they look like, and I can tell you they are not designed perfectly. There is still room for improvement. So later on, we will have projects, right? So you can work on the 2 autonomous robots if you like. Did we do the grouping? No, we didn't do the grouping. So we can do grouping later on. Or you can do something else. I do have a interesting topic that I really want to work on. It's so I will let you know right now. Keep set. Okay. Recently, I have discussions with researchers from actually Tokyo Tech. So he is working on so-called a cube satellite, cube-based satellite. So it's like a satellite that is not in a large size, quite small, and because it's small, so it's difficult to have enough energy on the satellite. So there are researchers who work on so-called the origami design of solar panels. Okay, so they fold the solar panel in the cube. So once they release it to the space, they will open the solar cell. So probably you have seen this in the past. They do similar things to cube satellite. So I'm quite interested in this topic, but it's difficult for us to really build one, and specifically for projects in undergraduate course. However, if you are interested, this is also some topic I would like to work on. So if you choose this topic later on, you can Google for so-called the origami design, and you can make drawings of this origami design, and you will learn finite element. You can apply a finite element to figure out what's the stress inside the origami structure. Okay, so that's also something I'm interested. I hope some of the group will be interested in this as well. Yeah. So next week we talk about some of the designs, and I will be starting to focus on components. I think the gear is the one has the longest chapter. Gear is quite complex, and there are many different kinds of gears. And during how many final element? Only one lecture, or two? I remember in the contract there's a 2 lecture, right? 2. If it's 2, does that mean one totally 3 hours or 2 hours? Do you remember? Okay, please go figure out about the finite element. So if it's 2-hour training, then I hope it's on the 29th of October. If the lecturer provides 3 hours, then the 30th, I can give the 30th to the lecturer. So after I introduce some robots and the software engineer comes here to show you how the software can be utilized, a week later you can present to us what you really want to work on. And you guys can get into small groups. I can talk about some rules about grouping. And then you will present your idea. And for the rest of the semester, you will be working with your team member to on the specific topic. And at the end of the semester, you will give a final presentation. Okay. I think I should move the progress report to here because I will be a judge. So I think I better do that. Yeah, so I'm sorry I changed the syllabus a little bit because on this week, November 26th, I am in Tainan. Is it? No, I'm in Taichung for to judge a competition. So I won't be in Taipei for the entire week. My postdoc, Dr. Patel, will help me to judge your progress report. So it will be a similar style to your proposal. But from the proposal to up to here, you have maybe 3 weeks. You definitely have work on something. So on this week, you will present to Dr. Patel, and he will give you some comments. And then you have 3 more weeks to work on the final project. So for this project, you don't need to do any real experiments. Most of your effort will be focusing on some analysis. You can try to analyze by hand, by computer, or you can use the software that we introduced you, ANSYS. Okay, so in order to use ANSYS, you need to make CAD designs, put in the ANSYS software. It will analyze stress distribution for you, basically telling you the von Mises stress. And you can even use it to compute the safety factor. Okay. I'm not sure if it helps you to compute the fatigue, but you guys can figure out. You can even ask the ANSYS engineer, can the software compute the safety factor for fatigue? Or the safety factor is only for static load. You can ask it. If the software doesn't do that, you can do it by yourself, because in our course, we have the knowledge of fatigue design equations. You can apply to it. However, there's always an issue between the reality and the simulation. I'm not sure if the simulator can estimate stress concentration. Maybe not very well. As I remember, when there are researchers working on stress concentration in software and experiments. And usually it's very difficult to use a software to simulate the effect of stress concentration. So sometimes the analysis you make will give you some results of the stress. Sometimes it's slightly lower than the reality, because in the reality there is some stress concentration. Okay, so I'm sorry, I have a meeting at the noon time, so I have to go. And today, just to remind you what we will cover for tomorrow, sure you have no problems with the homework. Are you guys okay with the homework? So if you guys are okay, you can just check in, and then that's it for today. I'll see you tomorrow for the exam.